Welcome back to the next video, everybody. Today we are finally going to take on the proof of Theorem 9. It's all that's left that we have to do in order to prove Langlands-Tunnell. So let's recall Theorem 9. Let's let F be a number field, and we'll suppose rho from the Weil group of F to GL2 of C is a solvable irreducible representation. Then there's a unique irreducible automorphic cuspidal representation, which we'll call pi of rho with local components pi sub b running over the places B of F of GL2 of the adels of F, such that trace of rho of Frobenius at B is trace of the local Langlands class at B for almost all places B of F. This is all we have to do now. Okay, well, we would like to apply the theory of base change to prove this. To apply base change to attack this theorem, though, let's do some investigating. Let's suppose up front, for the sake of argument, that given a rho from the Weil group of F to GL2 of C, there is a pi of rho of GL2 of A sub F. Okay. Now, just from the definition of base change, it must be the case that the base change lift from F to E of pi of rho is just pi of the restriction of rho to the Weil group of E. This is the definition. Remember, base change is trying to relate bumping up representations of GL2 of the adels to representations restricted down to smaller Weil groups. So this is exactly what we get by definition. And this holds for any cyclic extension E over F. So this tells us that if we start with a rho and we want to find good candidates for the pi of rho that Theorem 9 is claiming exists, we should pick an E, an extension E over F, such that pi of the restriction of rho to the Weil group of E is just known to exist A, first of all. And second of all, once we've done that, we should sift through all the cuspidal pi's such that the base change from F to E of pi is pi of the restriction of rho to W sub E. Okay, once you have a list, in front of you of all the available cuspidal pi's, you pick the so-called best one. We'll just say the best one. And what we mean by best will become clear as we go throughout the proof here. We'll call that best one pi sub pseudo of rho. PS here stands for pseudo. And then what do you have to do? You then have to prove that pi sub pseudo of rho is the pi of rho that you're after. Okay? The first of these two steps will involve invoking the trace formula, essentially. And the second one will use the theory of L functions. Okay? And then just a piece of notation before we go on. Given a rho from the Weil group of F to GL2 of C in a field E over F, rho sub E is just going to denote the restriction of rho to the Weil group of E. Okay, so what you have to do is you have to proceed in two cases, the tetrahedral case and the octahedral case. In this video, I will cover, just to keep the video a reasonable length, just a piece of the tetrahedral case, and we'll pick up on the tetrahedral case again tomorrow. So what is the tetrahedral case? This is the case where I'm given an irreducible representation rho from W sub F to GL2 of C, whose image in PGL2 of C, so mod scalars, is isomorphic to the alternating group A4. Okay, now A4 is a solvable group. Its composition series is the trivial group is a normal subgroup of D2. Dihedral group is a normal subgroup of A4. Just remember D sub n here is the dihedral group of 2n elements. So D sub 2 is the 4-element dihedral group. Okay, in other words, it's the Klein 4 group. Okay, well, look, you know A4 mod D2 is A3, but A3 is just Z mod 3Z, right? So that tells us that the inverse image of D2 in the Weil group of F under the map that sends WF to A4. So in other words, under the map that is rho followed by the natural map from GL2 of C to PGL2 of C. The inverse image of D2 in WF under that map has to be a normal subgroup of index 3, right? Because this quotient has size 3. Okay, well, that means it's the Weil group of a cubic extension of F. We'll call that extension E. In summary, we have the following diagram. So I have Z3 is A4 mod D2. That's what this exact sequence says. Then I know that Z3 is the Galois group of E over F. So this is an isomorphism here. I know WF is mapping to A4 because I'm in the tetrahedral case. Okay. Then I have that this group is size 3. So this Galois group should be this Weil group mod W sub E, where E over F is a cubic extension. This is some Galois theory, okay? Now, one thing that we'll just note here is that rho sub e is then monomial in the sense of proposition 3 several videos ago. Its image is dihedral, right? So it must be a monomial representation. Perfect. That's going to give us access to a theorem that we proved a little while ago. Okay, so what do we need to do? We need to find rho sub pseudo, right? Okay, here's what we'll do. Let pi of rho sub e be the automorphic cuspidal representation of GL2 of the adels of e attached to this monomial representation here. Okay. Now you might say, well, wait a minute, isn't that just what we were after? No. First of all, that pi of rho sub e exists because rho is monomial. That's theorem 6 from several videos ago. I still don't know that this is actually the representation I want, right? I know it exists and it's automorphic cuspidal, but I don't know that it's actually my base change lift. Okay. Now, this representation is Galois invariant because rho sub e is Galois invariant by construction, right? So I can apply base change, theorem 10 from the last video. What that shows me, though, is that unfortunately, pi of rho sub e is the base change lift of exactly 3 different classes of irreducible cuspidal representations, pi sub I of GL2 of the adels of F, not just one. Why 3? Because E over F is cubic, right? So there's 3 options. All right, but theorem 10 tells me more than that. Each of those classes is related to the others by a twist, by a character omega, or more precisely, omega composed determinant, for some character omega on this orbit space here. Okay, so in other words, if you just go back to the base change theorem, you'll see this. Pi sub I, the ith class, is pi sub j, the jth class tensor omega, or tensor omega composed determinant, if you want to be precise. Okay. Well, obviously these pi sub i's are going to be our candidates for pi sub pseudo of rho, but there's 3 of them. And so the question is, which one do we want? If you go back to theorem 3, so that's way long ago in the chapter, you see that the central character of pi of rho is supposed to be the determinant of rho. Okay. Now, the central character omega sub I of each one of my options, pi sub I, base change lifts to the central character of pi of rho sub e, essentially by construction. But pi of rho sub e is well understood, right, by theorem 6 and theorems before that. The central character of this guy is just its determinant, det of rho sub e. But what is det of rho sub e? It's just det of rho composed the norm map from E to F, right? Okay, perfect. Now look, essentially by definition of central character and this relationship here, the central character of pi sub I is just the central character of pi sub j times omega squared, where omega is my twist. I claim that follows immediately from unwinding definitions, and from this relationship here, I'll let you investigate that. Okay, great. I know I already lift to the determinant, and I know I already have this relationship between any 2 of my central characters. So the fact that I lift to the determinant tells me that at least one of the pi i's must have central character det rho. And then this relationship here tells me that exactly one of the pi sub i's must have central character det rho, because no 2 of them can have the same central character because the central character of one is essentially a twist by omega squared of the other, right? Okay, perfect. That's exactly what I want. I'll choose that specific pi sub I to be pi sub pseudo of rho. Okay, so we've picked pi sub pseudo of rho in the tetrahedral case. Next time we will show that pi sub pseudo of rho actually is pi of rho, the pi of rho from theorem 9. Okay, so I will see you tomorrow, and thanks for watching.